Okay, so this is the open discussion session, and my own perception is that we haven't had enough of discussion on some of the sessions, and so I thought that I will just talk about maybe at most 15 minutes or so for the theory part, and then we can have a discussion, and then I think Stan is going to do the experimental part. Is that right? Yeah. Okay. So the format for this theory part is going to be, I'm just going to make some just briefly opening remarks, and that's going to be a, lightning overview, and then there is one topic which is a more mathematical topic that was not covered in this discussion meeting, so I just wanted to briefly mention it. It came up in some discussions, and then really, in the discussion session, I'm not going to say anything unless people ask me specifically. I think this really is more about comments and questions that are addressed to all speakers and all other participants. So this is the whole idea about the open discussion. Okay, so let us begin. So in terms of overview, I do think that there is a spectacular transition that has occurred. I've been coming to India almost every year for many for several decades, and in the beginning, the general relativity community was really focused on completely mathematical issues and so on. And now, over the last few years in the IAG-RG conference, we see the influence of the gravitational wave detection, and that really has brought general relativity closer to other areas of mainstream physics, and that really is a spectacular transformation. And this is what Chandra had said in his address given to the 17th International Assembly of the General Assembly of the International Astronomical Society, that general relativity theory is a theory of gravitation, and like its Newtonian theory of gravitation, which it refines and broadens, its natural home is astronomy, and we are now sort of realizing it, as is clear from this discussion, and etc. But I think last night Stan Whitcomb told me a little story, which is very interesting, because when he finished his PhD and he went to ask Chandra for advice about whether he could go to join gravitational wave effort, this was in 1980s, a long time ago, and Chandra's response was that, well, we all know they exist, you will detect them, and so what? So even Chandra missed out the importance of this. So it's really refreshing that to know this, right? And this here would have been very surprised by this impact that the detection has had on astronomy, cosmology, and so on and so forth. And then the exciting upcoming decade is really fantastic, the 2020s, and particularly LIGO India is going to come online. So I'm focusing my remarks towards LIGO India more than just gravitational wave astronomy. And in particular, we hope that this, the idea was that the LIGO India detectors will come online in 2025. Now we're saying early 2026. But really important, as we heard from all these beautiful talks that in the last panel, very candid talks, how important it is. Otherwise, if it is delayed further, then in fact, the impact of LIGO India would be substantially lower. So I do hope that our community puts a lot of pressure on the leaderships and so on and so forth, that it really is kept kept to schedule, right? And also that the leaders really realize the importance of keeping to the schedule up here. I'm not commenting more on it because already we heard about from Fred and other people the importance of really getting this on in time. So what about longer term future? And here, of course, the important thing is, again, something that was discussed. We need to enhance creation of human resources for LIGO India. That is really paramount. And I'm going to just focus on the theoretical aspects because Stan will cover the experimental ones. And this really is what I had before I saw the program, I've actually thought we should be doing. Namely, on the theoretical side, there should be data analysis and source modeling, and then test of general relativity. And these two parts is what was in the black in Ajith's program, Ajith's slides up here, which really deals with general relativity itself or gravitational theory that as we know it, and the other things, namely the physics of nuclear matter in extreme conditions, applications to astronomy and astrophysics, and applications to cosmology. This is really kind of the major impact that we're having outside the areas. Now, first I had prepared some remarks to say something about each of these topics up here. For example, in the data analysis and source modeling, several people have emphasized the importance of improving accuracy. And I think the strongest statement I heard was from Alessandra, because she said that, of course, this is important for the next generation detectors as well as for the space-based detectors, but it's even important for advanced LIGO itself, not in terms of the events that have already been detected, because there the systematic errors are smaller than the statistical errors, but in terms of events that we might have missed out, marginal events. And if in fact we had improved accuracy, we might be able to extract more physics even out of the current detectors. Am I paraphrasing it correctly, Alessandra?
So in the next few years with advanced LIGO, not just now, but the problem will become even more critical, in the next few years. So with advanced LIGO, without going to even A+, I would say.
And I was very heartened that, we had this talk on nuclear physics, a very nice talk about nuclear physics. We had the talk from about the cosmology, not only the Hubble parameter itself, but other aspects of cosmology, like the first stars and the first galaxies. There will be both challenges coming from that, as well as information that gravitational waves can provide to the astronomy of these first objects. We heard about astrophysics, not only about the binaries, but also about how the binaries are actually formed, the formation mechanism. And there can be gravitational radiation in the formation mechanism itself, particularly for LISA. So all these are opening up completely new arenas, and that I think is very, very fascinating up here. And so this discussion meeting, the future of gravitational wave astronomy, covered all these areas, and this really, to me, illustrates the astuteness and the breadth of vision of the organizers. So that's really very nice. So the second quick thing that I wanted to say was one mathematical topic that was not covered, and this came up in various discussions, and I just wanted to do, this is to address to theorists, to be aware of this, because it seems to be somewhat ignored. Namely, as you know that the gravitational waves in exact general relativity, there was a lot of confusion, and that was resolved by this work of Bondi, Sachs, Penrose et al. In the experimental community, I think largely because of Peter Salson's book, one thing is that the big transition came with Pirani, and it did come with Pirani, but that transition had to do with just existence of gravitational waves. To extract astrophysics, to extract physics from gravitational waves, what this bead experiment really did nothing. We needed this whole framework of Bondi, etc. We used, for example, the radiation field psi4 naught. That's what numerical relativity computes, and so on. So where physics is, what energy is carried by gravitational waves, and so on, came from here. But this framework came with a surprising finding, and it was really a total surprise, both in the relativity community as well as in particle physics community at that time. And that is that even though space-time is asymptotically flat, if there are gravitational waves, then the asymptotic symmetric group is not the Poincare group, but it is an infinite dimensional generalization thereof, the BMS group B up here. And now this seems very surprising, because what do you mean? I mean, it's asymptotically flat. So the space-time metric is approaching Minkowski metric at infinity. The symmetric group of Minkowski metric is the Poincare group. So how can it not be Poincare group? Well, what happens is the following. The physical metric goes to as Minkowski metric plus 1 upon R terms of a certain type that Bondi's framework gives us. But this eta AB to which the physical metric approaches is not unique even asymptotically. I can consider another flat metric, eta prime AB, such that this is still true for a given physical metric. And so one might say, but what is the difference between eta AB and eta prime AB? Well, it is the following. Eta AB is completely characterized by its Cartesian coordinates, x, y, z, t. The line element is just minus dt squared plus dx squared plus dy squared plus dz squared. And the same thing with eta prime AB. Now, if it turns out that the two differ by each other from just a translation, I'm just shifting the origin, then eta AB and eta prime AB are the same, and the Poincare group is the same. But the 1 upon R fall off is such that they can also differ by an angle-dependent translation called supertranslation. For example, t goes to t prime coordinate up here might be t plus some function of theta and phi, and then say, for example, the x, y, z are the same, or you can keep t the same and change one of these x, y, z by an angle-dependent translation up here. And if I did that, then one can quickly check that even asymptotically, eta AB and eta prime AB are distinct. They differ in this 1 upon r terms up here. So they are distinct, and therefore, in this one, eta has its own Poincare group, and eta prime has its own Poincare group. They are not the same because they don't differ by translation. This is a non-trivial transformation even at infinity, and therefore we got a Poincare group here and a Poincare group here, and the BMS group can be thought of as a consistent union of all these Poincare groups. Now, the group is larger. Now, in the translation subgroup leads to the notion of energy and momentum. Similarly, supertranslation subgroup leads to the notion of supermomentum. But energy momentum has 4 components, whereas supermomentum has infinitely many components, as many as there are functions of angles up here. And for each supertranslation, we have got infinitely many balance laws. You know that for energy momentum, if I got the total Bondi energy at some instant, retarded instant of time u, and a Bondi energy at a later retarded instant, then the difference between them is the energy that is carried away by gravitational waves. The same thing is true for supertranslations. You might have supermomentum, which is defined by the supertranslation, that component of the supermomentum at a retarded time, and at another retarded time. These are 2 sphere integrals. The difference between them is a flux, which is a 3 surface integral, and this is the flux of supermomentum carried away by gravitational waves. So this is something that is well established long time ago, and that has been sort of made very mathematically completely controlled since the 80s. So the idea is the following, that we can use these infinitely many conservation laws to constrain waveforms. And this is the new idea up here. Now, how can this happen? Well, ideally, what one would like to do is the following, right? Ideally, one would like to say, I wish I knew the exact waveform in general relativity. And then you give me a waveform which comes from, say, post-Newtonian plus numerical relativity or EOB or phenom or whatever. You give me some waveform. That, of course, has some errors in it by construction. And ideally, what I could do is just subtract one from another and say, this is the error. But of course, we can't do that because we don't have the exact waveform. But no matter what the exact waveform is, it must satisfy these infinitely many conservation equations, these balance laws up here. Therefore, if you give me your waveform, which is the approximate waveform, I can check that balance equation. And if it doesn't satisfy that, there will be some error. And that error in satisfaction of the balance equation is a signal of how much the candidate waveform differs from general relativity. So the nice thing about this is that even with not knowing what the exact waveform is, you can calculate the errors relative to whatever the exact waveform in general relativity should be. So this is the idea that is in the first part of the first paragraph up here. So whatever the exact waveform is, it must satisfy infinitely many supermomentum balance laws, and therefore the deviation from this balance law for any given waveform is a measure of error or departure from exact general relativity. So for compact binary coalescence, we in addition have nice boundary conditions that in the distant past, the system becomes asymptotically stationary. What one uses in this analysis is asymptotic stationarity in the sense which is much weaker than that is used in the post-Newtonian analysis. And similarly, in the asymptotic future, we know that it approaches Kerr, so it again becomes asymptotically stationary. And if you assume this, then the infinite number of balance laws, together with this asymptotic condition, provide us infinitely many constraints on the waveform. So this is the H plus polarization, H cross polarization. So this combination is called sigma. It's the shear in Bondi framework. And what one is looking at this object up here. And the balance laws that I told you before, if I take this u to minus infinity, and sorry, u1 to minus infinity and u2 to plus infinity, just for simplicity, then the statement is that you get a balanced law, and that balanced law is just very simple. Namely, the total ADM mass minus the finest black hole mass, sorry, I forgot one line. Supposing the final black hole has a kick in the z direction with a velocity v, it could be 0, but that's rare, there will always be some kick. Then the total ADM mass minus the final black hole mass divided by this is the Lorentz factor, 1 minus Vc cos of theta because of the z directional kick up here. So this is something that you can just read out from the waveforms. And also the velocity of the kick you can read out from the momentum that is radiated from the waveform. So this is something that you know completely. And then must be equal to, the balance law says, the time derivative, retarded time derivative of this waveform, whole squared, plus some angular derivative of that waveform. This is called the eth, which is angular derivative. So this is a balance law, and this must be satisfied for every theta and phi, because I'm only integrating over u. So this doesn't depend on theta and phi, this just depends on theta, and right-hand side depends on theta and phi, and this is the waveform. So I got infinitely many constraints on this waveform. Violation of any of these constraints is an absolute measure of the error in the waveform relative to the exact GR. And the details are in a recent paper up here. So there are also, so this is simplicity, yeah. Yeah, so the post-Newtonian analysis tells you what this Gn is, and the numerical analysis, finally there's a Kerr black hole. The area of the Kerr black hole and the angular momentum of the Kerr black hole together, as Larry explained to us, that gives us the final mass of the black hole up here. And this V is given by calculating the flux from the waveform. You can calculate the flux of the momentum. That's what numerical people do, and that's what happens. I think there's a question, so maybe.
Hi, this is very interesting. Thank you. But I had one. I had one question which is a bit more philosophical. So, I mean, either phenom or EOB, we all know that they are not exactly the true waveform, which is the numerical waveform is supposed to be the closest. But the purpose of phenom or EOB is to make a close enough approximation in the sense of losing SNR for search and parameter estimation, which is a different question from are they true waveforms. So suppose we did this and found some floating point violation of this. How do we interpret that? Is that the right metric to use?
So the first remark is that you might have some ambiguity. I mean, you might have various choices, as Alessandra was pointing out. I mean, for example, with UOB, if you are going away from the parameter space where there are a lot of numerical results, there may be several choices. So one might want to make some choice to begin with, which waveform I prefer. So already there, one could use this to choose one or the other. Or you might have gluing conditions. Say post-Newtonian waveform is going to be glued to the numerical relativity waveform. There is some ambiguity as to where exactly I should glue, what the time interval is, should I do in the frequency domain, should I do in the time domain? So that will be useful. But your point is very well taken. This is, so to say, the first step. But the real thing is going to be to put in the information about the detector and so on, and choose this accuracy to provide some insight about what priors you should be choosing. And this is something that is not done yet, but this is something that Satya and Anuradha Gupta, and we're talking with these people because we don't understand the detector character. So there are two aspects to it, and thank you for asking the question. Okay, so this is the final thing. Okay, the last thing is that for simplicity, I just use -infinity to infinity. You can also look at finite intervals and get such checks on just the post-Newtonian waveform or just the numerical waveform. The expressions are more long, that's why I did not write them down explicitly. But in doing that, you need to know what is this wild tensor component of psi2. It can be calculated directly from post-Newtonian methods if your interval lies in the post-Newtonian regime. Or Larry just told me this happy news that there is a student who is almost finished finding what psi2 naught is in the numerical course up here. So once we have this, you can also have, for example, just around the time where you're doing the patching, you could just look at that little region and try to see if in fact one method is better than the other for patching. So these constraints can be used to discriminate between various strategies, as I just mentioned.
In fact, can I ask,
Please.
I think exactly about, so how, because I was wondering whether you also are coming out with some constraints, point-like, in the sense not integrating, and is this, so why psi2 is going to help in this? Can you a moment?
Yeah, so the reason why psi2 is coming is because really the constraint that you get has a psi2 here, but in the distant future, with the boundary conditions, psi2 is constant, asymptotically stationary case. These are the field equations tell you that, and that is why you just get Psi2 is constant in the appropriate rest frame of the system, and I'm just evaluating it in the past rest frame of the system, just for concreteness. I could do the other way around. And therefore, this is also, in the future rest frame, the Psi2 is also constant, but in the, when I convert to the past rest frame, I get the extra factor up here. So what one really needs is Psi2 here, except that in the asymptotic region, Psi2 is very simple. But the thing is that there will be too much error. You can shrink the interval, but if you really make it point, then there'll be probably, I mean, you can do it exactly here, there's no problem with that. But I think if you actually implement it numerically and so on, there would be some errors. So I think some finite interval, even a small interval, but a finite interval would be a better test of this. Okay. So let me just quickly finish. This I don't want to go into. I just want to say that the issue of angular momentum is also something that really is contaminated by super translations. And this has to do with the infrared or soft sectors in quantum theory. These ideas were completely worked out in general relativity community in the early to the mid 80s, but they have become very dominant now, this whole infrared sectors. And in fact, Ashok told us about not just the leading infrared effect, but sub-leading infrared effect, that those are calculated. And that all has to do with the super translation ambiguity. And the fact is that the super translation ambiguity then really introduces an ambiguity in the notion of angular momentum. You cannot just look at the initial total angular momentum and the final total spin and subtract the two. If you subtract the two, it is analogous to subtracting, for example, the z component of the angular momentum of time t1 and z component of the angular momentum plus some distance g times the y component of the linear momentum at time t2. I mean, the subtraction doesn't give you anything about angular momentum. So the same thing happens up here. You cannot naively subtract these two because these angular momentum refers to a different Poincare subgroup of the BMS group than this one. So you just have to be careful about angular momentum. So the last thing that I just want to say is that the enlargement of the four-dimensional translations to infinity-dimensional super translation group is forced by gravitational waves. If there are no gravitational waves, then the BMS group actually does reduce to the Poincare group, and all these ambiguities go away. So it really has to do with the presence of gravitational waves. But yet, somehow this fact has not been absorbed or has not been implemented sufficiently in the gravitational wave community, in the waveform community, and therefore using it provides a powerful tool to understand, to constrain the gravitational waves, but this has been largely ignored so far. We can have more discussion if you have questions, but I think I don't want to dwell just on this point. I just want to, yeah, please.
Yeah, so this is the super momentum balance equations. Does it modify the quasi-normal modes of black hole? No. So if you have a black hole which gets a kick after formation and it has that ringing, would you expect that these super translation to have some corrections on the quasi-normal mode frequencies?
No, they don't have any corrections on the super translation thing. Because they're all, the quasi-normal ringing is calculated just in one rest frame. This super translation really has to do with looking at what happens, it has to do with gravitational memory, which is really difference between what happens in the distant future and the distant past. Whereas here, super translation, the quasi-normal ringing just has to do with the different asymptotic future. So it doesn't really contaminate. Thank you. Okay, so this was kind of a detour, but since this topic was not discussed, which has to do with the mathematical aspects of gravitational waves in full general relativity, I thought I should do it. But now we come to this this more general discussion, all these topics. I think we have speakers and panelists for all these topics. So this is open for discussion. So please raise your hands and ask Satya. Satya is always good to start the discussion.
This is about your comment about LIGO India and coming, building LIGO India on time, on schedule. I still think that is important. That's very, very important. But one should not diminish the role of LIGO India in measurement of distance estimation. In the document which is in front of me, which we presented to NSF, what we showed was HLV, which is Livingston, Hanford, and Virgo, that distance estimation compared to ILV with India is at least a factor of 2. And this happens, as Stan has repeatedly said over many years, because LIGO India is not in the same plane as the other detectors in the Northern Hemisphere. And so that really breaks the polarization degeneracy. So we should not understate the advantage of LIGO India, even in the era, even if it's delayed by a few years. I know, I don't want to say that, saying that, oh, you can relax now, no. But the point is, LIGO India has always brings value. It is an added value that should not be understated. I mean, you can say we need to build LIGO India on time, but what is the advantage? What is the unique capability of LIGO India is what needs to be stressed all the time.
In all these discussions today, nobody mentioned Kagra, and I think we should bring in Kagra. But of course, Kagra, so that will be an additional detector, but as you pointed out, it is still roughly at the same latitude as the other detectors, and therefore LIGO India does do value-added thing. But my concern is that all these people in the room are so clever that they will figure out ways of looking at the data in a different way, calculating some other effect, so that, for example, that inclination angle ambiguity, which will be resolved by polarization measurements, might become less important. I just feel that these people are too clever, so that they will actually be able to bypass the current obstacle about localization and about polarization to large extent. So if that happens, then when LIGO India does come online, yeah, it will still give us better accurate results, etc. But it will be not the cake, it will be the icing on the cake. So I think we would like to really make a difference at a fundamental, at a major level. The discovery has already happened, but with respect to the inclination and so on, we would like to make
Yeah, but it might sound as though LIGO India will not have any impact.
No, that's
because when I say a factor of 2 in distance, that in order to achieve the same improvement of factor of 2, you need 4 times more number of sources. That will take 4 times longer time period. So what you could do without LIGO India, you could do in 1/4 of the time, is what I want to stress.
I'd just like to point out, to me, there is no distance between the emphasis I'm hearing from Abhay on schedule and what you're saying on the ultimate importance, because the real goal is the science. And this is a huge cosmological important measurement. And yes, it needs, ultimately it'll remain sensitive until it's solved. But putting off the solution for another year or 2 is criminal. Yeah, I agree. Right? So there really is no separation between the two.
I agree. Yeah.
One of the things which have been probably missed out in this meeting is the role of pulsar timing array to constrain very low frequency gravitational waves. So one would like to know how the LIGO group and the LIGO India group is interacting. For example, India also has a pulsar timing group called INPTA. How these 2 groups can be integrated with each other, because the timing array group, they are looking at very low frequencies. So it would be nice to have a coherent picture of 100 hertz to 1 kilohertz gravitational wave sources and the limits that is being put by the pulsar timing array group. So, I would like to know what kind of discussion is going on between 2 groups.
I can tell you my perspective. I don't know if that's helpful, because
I actually have a microphone, Sathya, so I'm going to steal your answer. Within the LIGO scientific collaboration, there are a number of people who work on both pulsar timing and on LIGO data analysis, because many of the data analysis problems share some common features. And it's been quite a fruitful back and forth on the data analysis things. a few years ago, this organization called GWIC, which is the Gravitational-Wave International Committee, which is an attempt to try to coordinate activities by gravitational waves groups around the world and across the spectrum. And a few years ago, we admitted into GWIC. It was originally founded by the bar detectors and the interferometers and LISA. And then the bar detectors have dropped out of that organization. The interferometers continue. Indigo is a part of that. But we invited the pulsar timing groups to join GWIC. They have. We've sponsored some workshops early on. And we did something in about I'm going to say 2013, which was a joint workshop between the pulsar timing groups and some of the people from the interferometer groups about what really would make a convincing first detection. Because it wasn't at all clear who was going to, at that point, which band would make a first detection. And we wanted to actually probe that idea of finding out what would our colleagues find comfortable. So those two groups have actually had some good interactions, and I hope we'll continue to do that.
Yeah, Stan has covered some of the aspects, especially on the data analysis side. But one scientifically very important aspect is the pulsar timing array detects both the so-called Earth term as well as the pulsar term. And that really gives them a very powerful way of testing generativity and so on. Now, something similar happens in multi-band gravitational wave astronomy. If you use LISA and ground-based detectors both, then you have a very long arm, and that helps improve the science that we can do. And we are beginning to understand the techniques that they are using. So this time, we are borrowing ideas from pulsar timing array to better understand. So this interaction and working together is extremely important. It's a shame we didn't invite any IPTA or ILPTA. Yeah, we didn't. Yeah. Okay. Yeah, we should have got that. I mean, it's our fault.
Yeah.
No, I just wanted to say, Bhalchand has been involved with the Indigo consortium quite closely. He was on our advisory board, and he's an NCRA, so there has been some level of interaction. In particular, I think we have used their radio astronomy schools to start giving gravitational wave lectures in that, and they have a very good program for that. Beyond that, there has not been a scientific interaction, but I don't know if Sukant has anything more to add to it. I mean, do you know?
More importantly, you could get their engineers, for instance, people who work building GMRT.
Yes, so the only problem is NCRA is heavily into SK now, and they upgraded their GMRT. So it's not easy to spare engineers and instrument builders in the country, given that our numbers are very low, is very difficult. But yes, I mean, we have been in touch, but I wouldn't say extremely fruitfully, but we are aware of each other's.
Okay, Sukanta.
Yeah, so just to echo what Tarun said, so yeah, we have involved people like Bhalchandar in our, LIGO India, the road ahead meetings. Plus, on their side, there was a IPTA meeting in Pune in June, and they had also invited some of the people, at least from the LIGO side, into their meeting. So yes, we are talking, maybe we should talk more, and we'll be mindful of this going into the future. On the science side, the fact that the pulsar timing arrays have severely constrained or put upper limits on the background on gravitational waves from, say, supermassive binary black holes, says something about the type of rates we may expect from SMBH mergers in LISA. I'm not, which is perhaps useful at some level, but I'm not sure if, apart from data analysis techniques, we are already learning something from pulsar timing array upper limits for LIGO-like science? If somebody knows an answer, I'll be interested.
The kind of masses they are dealing with is much higher, typically. It's nanohertz gravitational waves, so 10 to the 8, 10 to the 9 solar masses. I think there can be extrapolation from that band into other band by using some power law to learn about LISA, but I don't think the two are at the moment being done. Yeah, it's worth looking at it.
Tarun has a comment.
Quickly, I wanted to add that one area where definitely these different bands come together is the stochastic background. And it's very important to keep an eye on each other's work. Unfortunately, I think Sanjeet has already had to go back, but I am aware that particularly in the stochastic gravitational wave thing, there are signals that span all these bands, and that's an important place to be talking about it.
Okay, so perhaps other questions on all the list of topics that we have? We'll go on another for, yeah, please go ahead.
How to know the true waveform? From the great deal of the discussion that we had, actually, it appears that it might be an impossible thing.
No, I mean, if you knew the true waveform, then one would not need anything, right? One would not need post-Newtonian approximation or so. No, we don't know. I mean, there's no, we don't have any idea about how to get the true waveform, right? I mean, we only, everywhere, right?
Everywhere, because I mean, numerical relativity can provide some waveforms which are quite accurate, limited by length and parameters, etc.
Other comments, questions? Yeah.
I'm just trying to understand the supermomentum balance because you have particularly drawn the attention that if there are gravitational waves, your Poincare symmetry is enlarged. So we know that there are stochastic gravitational wave background, they are ubiquitous. So in the presence of stochastic gravitational wave, do you expect some more effects on the kind of the momentum, supermomentum balance and the resulting modification to the mass in the presence of stochastic gravitational wave background? So, some additional corrections?
So there are two sources of this stochastic background. One is going to be just something that happened, say, during inflation, so the very primordials. And the other one maybe there's a background created by something like supermassive black holes. So these considerations of all the things that one uses in the gravitational wave, in the gravitational wave community as opposed to cosmology community, has to do with these isolated systems, which are sort of modeled by being asymptotically flat and so on. So for isolated systems, the supermomentum, so as far as the supermassive black holes are concerned, these considerations apply, absolutely. But really, the primordial gravitational waves, right, which really, say, for example, happened because of the vacuum fluctuations, which got expanded. So those ones are really different because they are not solutions to equations with the right-hand side of Einstein's equations, right? There's really different. It's not that there is a body which is really doing something and then creating, because they came from these quantum fluctuations and then are very well described by classical general relativity at later time. So they're qualitatively different. And the interesting thing is that in the cosmological context, we really do not know what gravitational waves are in the full nonlinear general relativity. We only know it in the linearized approximation. So the two analyses sort of get separate from each other. So for the primordial ones, there is no, it's just a linearized theory and so on, and then one doesn't, on a cosmological background, and then the supermomentum, etc., is not relevant. But for the ones which are called supermassive black holes, they are relevant. Can we, yeah.
It's about one of the other topics, the data analysis. I think there was talk about machine learning. I wanted to ask if those machine learning techniques have been applied to long in spirals and what the status is. And secondly, whether these techniques are able to estimate the significance of events, namely measuring what the background rate is and assign false alarm rates and so on. If there is somebody who has worked on that,
Yeah,
I
great.
know
Yeah.
there are at least two people here.
So with regards to the first question about looking at longer signals, so the groups of which I was one of the groups, we were trying to do proof of concept. So we're looking at short binary black hole signals to prove the concept that machine learning can match the sensitivity of traditional searches. We have not gone on to look at longer signals. It's something we might do in the future, but I know that other groups are, and I get emails all the time with people saying, we're trying to reproduce your work, and we're trying to extend the length of the signals. And it's a matter of time before that is put in place.
Okay, since you thought about that problem, can you tell us what kind of training might be required for longer duration signals, but because there's a greater variety of these longer waveforms. You know, binary black holes, they're short, not many different types. So what's your take on that?
So there's a sort of standard sort of statement in machine learning is if you want to do better with your machine learning algorithm, show it more training data. And we find that that is the case with all the problems that we look at. And it's going to be even more the case. It's related to the density of templates that you need in the match filtering approach. So moving to BNS, lower mass kind of signals, you will simply need more training data. I think it's positive, the fact that we were able to do it for binary black holes in a matter of hours on a single gaming GPU, right, that people have in their home computers and play games on. So the prospect of doing far harder things, I think it's entirely doable with the effort and expertise in our community and surrounding it in the computing community. Sorry?
No, you can repeat the question. Larger training set may jeopardize the efficiency of the search or the time it takes?
No, well, so it will impact the time it takes to train. That's the one great thing about these machine learning, most of the machine learning algorithms and approaches is that you spend all the time front-loading the analysis. It can take a long time to train. I'm not going to lie. It may end up taking a long time.
Worry. That is my worry for long.
But then running it is milliseconds.
That may be the case. However, I do worry. Okay, second question was about the background. Can you say something about background estimation, machine learning?
It's something I've thought less about, and somebody else may be able to say something deeper on this, but I think ultimately it's going to come down to your understanding of the data, right? And we have, everything up till now has been trained on Gaussian data, simulated Gaussian data, so you want to train on real data. That's one thing we want to do next, is start putting in old LIGO data in to train it so it knows what it's seeing, but you're still limited with the amount that it gets to see. We only have 3 or 4 years worth of data to train on. So you won't ever really be able to make statements about false alarm rates beyond that. I mean, our existing methods are cheating. You know, the time slides when we say 1 in a million years, it's not. It's an extrapolation.
No, it is. There are other methods. It's not just the time slides. But I think that is an important development that needs to take place. And if you can show that you can detect the current event list with the same confidence, that's when people will buy into it. That's my feeling.
Is there another question in the last? Maybe this might be the last question before we go to Stan's session.
This is a response to Satya's statement that if you can show that you can detect current events with the same confidence, people will buy into it. It has been shown not for machine learning, but for human learning. Right?
We completely appreciate that. Yeah, absolutely.
But I don't see the second part happening.
This is a process. The process will happen, and we are already talking, right?
No, I'm not. I don't really see any meaningful crosstalk.
Okay.
This is my perspective.
We should increase that. Okay.
Okay, so this is a good time to switch to experimental side of the discussion.